MapReduce lets you process very large amounts of data in a distributed fashion. It was first developed by Google in the mid-2000s as a method of aggregating data by processing increments of your data at distributed points, then sending the results from each point onward to be updated again. An election is a MapReduce problem. Each voting station sums up the local results and sends it to the regional location where they send all the results in the region to the head office where they sum up the total tally. MongoDB uses MapReduce to handle aggregations. RavenDB uses MapReduce in a slightly different way to allow you to handle updates to your aggregations over time. Let's get ready to rumble! Today, we will compare the two databases to see what happens when you need complex aggregations. What happens when you need aggregations that get increasingly complex over time as your data store expands. Database developer and Microsoft MVP Oren Eini will take you on a tour of MapReduce aggregations at a large scale to determine which option delivers performance in real time for producing sum totals, averages, and more. You will learn how MapReduce works, how you can do complex computations over time at high performance, the difference between RavenDB MapReduce and MongoDB MapReduce. Feel free to ask questions by clicking the Q&A button at the bottom of your screen, and Oren will be happy to answer them throughout the session. Enjoy your presentation, and here's Oren.
Hi, everyone. So MapReduce is a really interesting problem. Officially, the MapReduce for distributed operation has been around since the early 2000s. But if you look at the source of the name, MapReduce has actually been used in functional languages as an aggregation method for literally decades. I think that the earliest reference I found was somewhere from the 60s. And it's interesting because when we talk about MapReduce today, or it used to be the case that everything had to be MapReduce, and MapReduce was the big buzzword. But when we talk about MapReduce today, we tend to talk about, okay, how do I aggregate data, sometimes low data, in as efficient a manner as possible. Now, this webinar, I'm going to focus on two separate topics. The first topic is here. How is MapReduce actually implemented? What are the things that you need to understand, especially as relates to RavenDB and Mongo? The other thing that I want to talk about is the journey. Where do you actually utilize that? What are the implications? Everything around the practical realities of actually doing those sort of queries in production on non-trivial datasets. Which brings us to an interesting problem. What is a dataset? Actually getting non-trivial datasets that are interesting to work with is a problem. There are a lot of public datasets. I chose the Enron emails. If you're not familiar with them, Enron was an energy company, been around for 30 or something years. And at some point, they decided that they want to deal with fraud. The story is really interesting. Effectively, they bought some stuff, dark fiverr basically, and they decided it's going to be very expensive, and they put in their ledgers what they thought this is going to be worth as assets. And then they leverage that to say, oh, we have this huge asset pool, let's make some more money out of that. And this becomes really interesting if you're an accountant. The end result of the Enron story was that it went bankrupt. One of the major accounting houses was dissolved as a result of that, because apparently they were very helpful for committing financial fraud. Some people went to prison, and the most important from my perspective is that we got 517,401 emails, which is one of the largest natural text corpuses around. So yay for voter fraud and cool data sets, apparently. Not voter fraud, that's a different data set. I'm talking here about investors fraud. Anyway, let's talk about the data. The actual Enron data set is a set of files using the MailDir format. It's not really that interesting, so I pushed that into JSON, and I got the following. In Mongo and RavenDB, we got this data. Let's look at the actual data. This is inside of Raven. And here you can see an email, and apparently Sandeep moved to Houston, or move someone to Houston. And there are quite a lot of these documents here, and you can see that the format is effectively email. Form to text, some headers that might be interesting for analysis, etc. So far, so good. Now, what's going on with Mongo? And for Mongo, there are a lot of clients. I use the official one. This is apparently what the official one, and this is how you can look at the data. 517,401. I hate math English. It doesn't feel right to me. And then we get to a document that looks like this. And that's about it. That's not really that interesting. Something that was interesting to me was I found that there is this huge discrepancy in the database sizes. And I wanted to investigate why, and then I realized that we have this issue. RavenDB does pre-allocation of this space. And it does that on a gigabyte boundary. So the moment that you get to 2 or 1 gigabyte, we'll already allocate the next 3 gigabyte. The reason we do that is for performance and optimizations, but in our case, what happened was that this resulted in somewhat of a surprise for me. We're still seeing a larger data size. And I thought to investigate why. And then I started saying, you know what, I don't care about that. I care about this new feature that we have, which is called documents compression. And I'm sorry, there is no UI for that, but it goes like this. In the database record, you're setting this, and we're probably going to have UI for that in the next week. But basically, it is that I'm going to say, you know what, I want you to compress the collections document. And when you compress the collection documents, something really interesting happens. We're now at this. So just to compare 871 megabyte versus 2.01 gigabyte. So we reduced the disk size by more than half. And this is interesting. RavenDB does a lot of cool stuff with adaptive compression, learning from the actual data that we have, but that was just a side note. I'm probably going to cover this in a future webinar in more depth. Now, let's talk about this. Now that we have the data set, which is effectively emails, we now need to start asking questions. Now, I wanted to be somewhat fair in this webinar, so I didn't want to come up with my own questions. So I went to this book, and it has a chapter on Enron that shows some possible questions that you can ask. So I decided, you know what, let's go with that. And you can see here, this is the questions that we're going to ask. Some of them are very classic MapReduce operations. Some of them are not. Finding dentro is not really a MapReduce operation. But before that, let's talk about what MapReduce is, because I assume that you know what it is, and that's probably not necessarily the case. MapReduce is a way to do aggregation of data. Effectively, what you're going to do, you're going to run 2 steps. In the first step, you're going to map over the data. You take the original data, you apply some function over that, and you get some output. The output has a key and some additional properties. For example, if I want to find all of the users, all of the emails based on a particular sender, I can emit the original, the sender email as the key and the count of the emails as the value. That gives me a huge list of key and values. I'm then able to take the reduce and aggregate all of the values that has the same key into a single output value. That's the reduce part. Now, MongoDB used to have the classic MapReduce system. At some point, they replaced that with something that they call aggregation pipeline, and they currently recommend that you use the aggregation pipeline over MapReduce for most scenarios. RavenDB had MapReduce from the get-go, but it does that in a very different way. Let's talk about what MapReduce is. What we have here is the number of emails that were sent in a particular date and month. Oh, sorry, a year and month. So 18,763. The way that it works with Raven, MongoDB works slightly different, and we explain how, is that here the emitted values for all of those. You can see for this document, for 6/2001, count of 1, and here is the total number across the board for this particular value. Then we have 14 here, 6 here, we need to aggregate those as well, and we get to the final tally. Okay, you've seen only the presentation. I don't want you to see the presentation, I want you to see the screen. Can you see the screen now? Okay. Okay, I'm sorry about that. Let me go back and show this. Okay. Now you can see two documents. One of them from June 1, one of them is from July 1, and both of them are showing some aggregation of data. And here the output from the system. So all of the documents here, 909 in total. We aggregate them in conclusion, and now we see that in May of 01, we have 35,000 documents, emails that were sent. The whole idea with MapReduce is to first map the results. Here are the results of the map, reduce them, and then you can reduce them again and again and again. Remember the election problem? This is a MapReduce operation. In the election problem, we run a map. We count to which candidate people voted for. And then we take all of those votes and we aggregate them so we know what is the total tally for this voting station. And then we send it to the region and they do the same operation, the same reduction, and then they do that globally, and here is the final results. So what's the major difference in aggregation semantics between Mongo and RavenDB? And the key here is when this is running. RavenDB has two modes for running aggregation. One of them is the classic MapReduce. This is what we see here. This is happening when we create an index. And once this is done, you're able to do all sorts of interesting things on top of that. The other side is that we're able to do dynamic aggregation. This happens at query time. With Mongo, on the other hand, we have aggregation pipeline or the MapReduce operations, and those always run at query time. Now, running at query time is an interesting choice because at this point, you're paying the full cost of the aggregation. Now, this aggregation may be really expensive. If I have a lot of data and running some sort of non-trivial aggregation, I may have to wait for a while. So the typical way that you solve that with Mongo is that you run the aggregation and you output that into a separate collection. So then you have a view of the data that you can then manually update down the line. But we'll touch on that later. For now, let's go and start seeing real queries. Here are two queries to find all of the emails in date range. RavenDB uses RQL, which is the Raven query language. MongoDB call it MQL. I don't think this is much of a language, but no one asked me. The key issue from my perspective is that what MongoDB asks you to do is build the AST, the abstract syntax tree of the query manually. And this works as long as you have relatively simple queries. When it gets to complex ones, then it gets to be a chore to understand what's exactly going on. Another thing that you have to remember in this case is you have to create the index. If you don't create the index, Mongo is going to do a table scan or a collection scan. And a collection scan means exactly that. Let me read one document at a time over and over and over until I find all of the relevant results. if I don't have an index, the cost of querying the collection is O(n) of the index. If I have an index, probably the cost is O log n. With RavenDB, you don't need to create an index. RavenDB is subject to the same realities of Mongo in terms of computational complexity. But RavenDB is going to create the indexes that it needs on its own. You don't have to do that manually. Now, let's look at another example. Let's find distinct senders from all of the emails that we have. So let's look at the Mongo example and see what we have here. Now you can see here is form. And for some reason, the API that I used form as an array. Apparently in email, you can have multiple form senders. I don't know how that works. Maybe if you're working on a group or something like that. But that means that, and for some reason, I have no idea how you can execute queries here. If you want, there is something like this, but that's not really good for what I want to do. I want to be able to do this. So I can do something like this. Sorry. Use Enron. And now something really interesting is going to happen. You might not see that very easily, but what I actually got here is an array of is a list of the distinct arrays that I have here. That's not exactly what I meant. In order to actually execute this, I have to run this. Okay, now notice something interesting. I hope that you're able to see the time it takes to answer the query. Thus, once I have the result, you can page it quite quickly, but this takes a while. Now, the reason this takes a while, it has to go through the entire data set, 500,000 result sets. With Raven, on the other hand, we have a different issue. This is how we use that. We have to quote the data in order to get the appropriate in, because form is a reserved board. And here's the result. Now, you might know, we have decided to make performance something that is important to us. So what we've done was make sure that we see the performance cost. So let's make sure that we are not using any caching, and here are the results. So we're able to render that in 10 milliseconds. Now, the reason we can render that in 10 milliseconds is not that I'm able to go over that list quickly. It's that I don't need to. If we go here, you can see that, okay, we run this query, and now we have this index. And this index is a MapReduce index, which for some reason does not want to go. Okay. Here is the MapReduce index. Okay. For some reason, I think I messed up the visualization. Okay, now let's see here. And now you can see here all of the distinct items. Get it merged here. So now you can see all of the documents that have unique names. Now, if you notice closely, you will see that we have this array here. This is an instruction to RavenDB. You know what? I want you to project not the array, the values of the array. I can also do this, in which case I get the distinct arrays that I got here. Good enough so far. We can already see that there is a major difference in the approach to handling aggregation. Now, in RavenDB's case, we're saying, okay, group by the projected form and unwind the array. And here you're doing that manually. First, go to the form array, get me a a value per one of the values and then group them by the form. Okay. Now, here is something that is slightly more complex. Kenneth Lay was the CEO of Enron, and apparently he didn't send a lot of emails. But I want to count how many emails we sent to him, or was sent from him. Now, here's what's going on. First, get me all of the emails sent by Kenneth. Then, unspool the arrays from form and 2, project just these two, group by the form, and create an array of the two. This is what this looks like. Second. And here are the results. I think I prepared in advance for that, and I have, there we go. So for some reason, you can do something like that in, no, not this one. Not this one. No, that's the wrong thing. Wrong thing. I did not, I thought I prepared for that, but apparently not. So this query, you can see gives us the ID of Kenneth. By the way, I don't understand how you cannot do proper queries here. It's just crazy to me. Anyway, and here are all of the people that he sent emails to. That's interesting. Now, let's see here how I'm going to be able to do that in Raven. Now, what about that? This works because I don't have a lot of users. I don't have a lot of emails from Kenneth outward. What happens if I did have a lot of emails out? In this case, I'm going to say, instead of the CO email, let's go and do the same thing. But I did that, I don't think that you caught that, but that was with the Outlook team, which apparently sent a lot of emails to a lot of people. So that works, and that works great. We will see exactly why it works great in a second, but I think that it makes sense what's going on here. Let's see how we handle that with Raven. Oh yes, before that, this is how you're supposed to write that in C#. It took me an embarrassingly long amount of time to translate between the two, and I think this is just annoying to have to do that. With RavenDB, you cannot express the query in the same way. Instead, and why is that? Because we intentionally keep the query language as simple as possible. If you want to do more complex stuff, do that in the index. And let's see what we exactly did in the index. Here's the index. We have two stages, from the map and the reduce. In the map, we're saying, okay, for each one of the forms, output the emails that we're sending to and give me the count of them. And now here, I want you to group by the form. Get me, merge all of the twos that this form sent to and create a distinct on them and get me the total. The end result is that I can run this query. And the query is immediate. And it's sent to 994 people. But notice what we have here. This is a lot more interesting query. And this is because of the way RavenDB builds the queries. Let's see this. RavenDB, when it built the index, it indexed everything. So asking questions such as, okay, who sent the most emails? Outlook team. And apparently David Foster was quite a heavy writer. If I was trying to do something similar with with Mongo, you can see here that I comment on this, and I want you to notice the time that it takes to respond to this. So let me just remove the match, and basically I'm saying, okay, I want to group across everything. It takes a while. It takes a long while to get these results. And RavenDB is able to give you these results much more quickly because, again, we don't have to do this computation. We've already done that and paid the price, and now we are ready for that. Now, remember that earlier I checked with the Outlook team and it was fast on Mongo as well. Part of the reason that it was fast was that the number of emails that the Outlook team has sent is just 1,500, which is negligible amount in the grand scheme of things. The idea here is that Mongo gathers all of those 1,500 documents and then run it through the pipeline. The catch here is that when you have a lot of items in the pipeline, you're going to have to wait for the whole thing to happen. And you can see that I can keep on talking and talking. It takes seconds to get something done. Now, this is again with a data set that is very small. 500,000 documents is not really that interesting. And when I have just a single query running, the impact of this difference in architecture and behavior when you have large data sets and you have lots of queries, and especially if you have both of them, is very significant. Now, let's see another good example of what we can do. Okay, Mongo has some full text search indexes, or some let me rephrase that. Mongo has some full text search features, not indexes. And the reason for that is that you can see we're finding theme that goes with poker. It's poker time, etc. Now, the way that it works, Mongo allows you to define a single full text search index on a collection. In this case, we index the body and the subject fields. Now, why does it matter? It matters because you can see that there is a difference in how we express the queries. And here we're saying, okay, let's in the full text search index, let's search on the phrase raptor. And here we're doing something different. What are we doing here? Let's look at that. Body, let's go to subject. Oh, you know what, I don't even need that. Now, you will notice something really interesting here. Apparently, Sharks really likes poker. I have no idea from this data, but again, I am going to make inferences. Now, notice that the query that we have here is interesting because of how we express it. I'm going to say that, you know what? I want you to query on the subject, but when you find something on the subject, I want it to be twice as important as if you found it on the body. And that allows me to do more granular work in a much more interesting fashion. RavenDB also allows you to have multiple full text indexes and stuff like that. But one of the interesting from our perspective is that once you've defined your indexing criteria and how you work, you're not limited to that. MongoDB has some advanced features that allow you to say, oh, terms on the subject are more important than terms on the body. But this is fixed at indexing time. And indexing this data set takes quite a while. And okay, by the way, for some reason, this takes quite a significant amount of time. I actually checked that, and I think that we take, where is the full text search index? Here we go. So we take more. Okay. The reason we take more is unfortunately that we use Lucene, and Lucene is doing, again, pre-allocation of data, and it makes sense to handle it this way. The really interesting, by the way, another design choice is how we utilize the system. RavenDB tends to say, oh, I'm going to need these resources. Let me grab them in advance in such a way that is going to allow me to utilize the most out of the system. What do you mean by that? For example, if I need more disk space, I'm going to grab it in advance and grab a big chunk of that. I don't know if you remember, but there used to be a huge issue with disk defragmentation. And it still is the case that this matters today, less so than when we all run on speed in Rust, but this is still an issue today, and RavenDB makes it easier for the operating system to do the right thing for us. Now, this is where we get something really interesting. I want to get count of messages by date. This is what you need to do in Mongo to do that. So for each of the documents, project into the date bucket the year from the date, group by the year and the month, and give me a count of everything, and then do a sort of the data. This is what you need to do with Raven in order to handle that. Just to compare, let's run this query. And here's some results. By the way, this was really surprising, but apparently we got this in the data. And again, with RavenDB, really surprising this. Oh, and also we have this, which was also very fun. So someone sent the data today. Oh, still in the future. Again, and I want to focus on this again. RavenDB ran this and created appropriate index. This index, and we can inspect it here by date and month. Now you can see 3 different dates and how they're being aggregated. Now, the key from RavenDB's perspective, when we query, we're not querying this thing. We're not querying the half a million results that we have. We're querying here. We're querying the final tally across the whole board. And because we already done all of the heavy lifting stuff, we're pretty much done. 0 result. I had to, by the way, I had to disable the caching because with the cache it was showing the old result of how much it took me to get the data. Now multiply that by some interesting number of queries, increase the database size just a bit, and you're going to get into interesting situations. Okay. By the way, I'm counting on a lot of questions here, so take that into account. The major differences that we have in the approach for aggregation and queries in general. RavenDB favors moving as much as possible to the indexing time. MongoDB would, aside from some work that you can do in indexing time, most of the costs are going to pay them at query time. The issue here is that you tend to have lots more queries than indexing. So with Raven, you're going to see far less cost because we only pay the cost of doing the work once, where with Mongo, you pay that on an ongoing basis. It is actually very visible when you start thinking about, okay, let's say that I wanted to show you the number of messages that you saw per day, and we had ongoing writes on the database. With Mongo, in a large data set, you would end up not being able to run the query effectively because it would be too costly. So you can spill the result of an aggregation query in Mongo into a collection. And you can even merge an existing collection with an old collection, but the issue here is that now you have to do lots of things manually. You have to make sure that you don't overlap date ranges, that you run it on appropriate schedules, also stuff like that. With Raven, all of that is managed by RavenDB. We also have a major advantage with regards to how we structure the MapReduce index. And if we go here, it will be very visible. There we go. Let's imagine that I have a new value for November 2000. What's going to happen? Well, I'm going to have to edit here, somewhere at the bottom of the list. Update this number, then update this number. And in 2 or 3 operations, I'm done. And now the value is ready to be queried. And all of that means that as the size of the data grows, the amount of work that we do actually gets reduced, which is funny, but if you think about the computational cost of tree traversal, we actually have a cost which is O log h, where h is the height of the tree. And if we have massive amount of data, massive, this is probably going to end up being hundreds of leaves here, then we're going to open up a new level and continue compute data in this fashion. That makes me really happy because the computation costs are amortized and the queries are really fast. And here is time for questions. I think that I spoke way too quickly, but hopefully that was interesting for everyone. Questions, things you would like to know about MapReduce in RavenDB and in Mongo, or in general of the differences between these two databases. And Iwut is saying, thank you very much. Absolutely, and pleasure to have you here. Okay. Going to give you a few more seconds to answer the question, to ask any questions. In the meantime, I want to, so we have a question from Matthias. Where indexes are used in Mongo? So you can see here, those are the indexes that are defined. I defined it on from, date, basically anything that I intended to query to make sure that to make sure that the comparison is fair, because RavenDB would actually generate the appropriate indexes on the fly, and I wanted to make sure that it works. So I think that you're able, so you can do something like this, and the queries, and do an explain, something like that. At which point you can see that, okay, the text index returns some values, we fetch them, and something like that. If we go and look at somewhat more interesting query, let's say, wonder if I can do this. No, I can show it here. So let's do something like a from cannot let Aaron. So here's a query, and you can see that here are 36 emails that he sent. And this was fetched from the query, from the index. You can do that because you can see index scan. Now, if you go on the other side from the two, this was much, much lower. And the reason it was much lower that it has to do a full scan 517,000 documents, very expensive, blah, blah, blah. You don't use queries explicitly in Mongo. There is the query optimizer that does that, but you can see that they won't know about that. That's something bad. One of the other differences that is important to understand, when are indexes updated? Indexes updated in Mongo when you modify the data. One of the reasons they have this fire forget method of writing to the database. Raven, on the other hand, accept the data, write it to disk, and we can actually probably see it in the IOStats. We write it to disk, and only then are we going to go and update the index. Now, why does it matter? It matters because it means that you're not held up waiting for the transaction to complete, for all of the indexes to complete. That means in turn that you're free to use more indexes. Because typically when you're using indexes, something really interesting is happening. You have a choice. You have a choice between having more indexes, which means that your queries are going to be faster, but your writes, your insert updates are going to be slow. On the other hand, if you have less indexes, then your writes are faster, but your queries are slow and sometimes much, much slower. And that can be an incredibly tough choice to make. One of the things that we have done with RavenDB is look at this indexing strategy and reject it. We said, you know what, it doesn't make sense that we have to do this either or option. So we decided to do something different. And what we did was move the index execution into the background. So you make a write, the server get your data, persist it to disk, and then immediately acknowledge that. The index was not even involved. At the background, the index starts running, indexing your data and updating itself, which is great. Then, and that's it. That's a whole different architecture. But it has some really, really important implications. Let's talk about some of them. The first of which is that because we are not tied to your transactional behavior, we are free to optimize ourselves accordingly. For example, let's say that you're updating your data 2 documents as a second. If you're running indexing at write time, you have to update the index on every single update. And that's horrendously complex. Not complex, also costly. It's complex to make this efficient. And the way that RavenDB does that, we're going to do that in background, which means that we don't have to do that once every write that you make. We're free to say, here are the last 10 changes that you've run. Let's index them in a batch. Now, if you have 2 documents, 2 writes a second, it doesn't matter. If you have 5,000, it matters quite a lot. Because then instead of having to do 5,000 individual index updates, RavenDB is able to do 5,000, a batch or a single batch of updating the index with 5,000 documents, which has a huge impact on the overall throughput of the system. Another factor that we do is that we limit the amount of resources that indexes can take. So with RavenDB, indexes are actually limited from using too much CPU. Let's say that I have 100 indexes on this database, on a database, and all of them are working. If I'm running that on a reasonable machine, that means that I'm going to see 100% CPU. With RavenDB, you're probably going to see something like 75% CPU. We're going to keep a core 2 free, not do any indexing on that, specifically for the purpose of allowing you additional compute resources to answer queries, to run the other things that RavenDB does, all of those sort of things. And because we have this approach, then you're much more free to decide, now I have to make a change. I need to wait for it to actually be indexed. And you can do that either at query time or at write time. So you have a lot more freedom. Another really interesting factor that we have this approach. We can say, you know what? I don't really care about this index. I really care about this index. And RavenDB will prioritize the indexing on both of them accordingly. So you don't have to do that manually. So, this is an index on a report that gets used once a week. Okay, let's make it low. Let's make sure that it's not something that is going to take critical compute resources from the system. I hope that this answered the question. More questions. I really like these open-end discussions because it allows me to touch on things that I might not necessarily thought to speak about. As long as we're talking about indexes and I'm waiting for additional questions, here are a few things that you might be interested to know. Everything in the database, everything in RavenDB is tracked. So you can see here all of the index, all of the individual cores that you have on the system. Let's go here and let's force RavenDB to recompute this. And we're going to go here and see what it does. So it processes at a rate of 30,000 per second. Here are the relevant cores that I have, exactly what's going on, all sort of stuff like that. In terms of visibility into exactly what's going on, and come on. Okay, so the entire indexing run here took 21 seconds to do everything, and we can dig down into that. There's also additional things that you can do. You can look at the IO reports that we have here, stuff like that. Any caveats with either RavenDB or Mongo in clusters? RavenDB in a cluster form, you have to understand that it's running in a multi-master setup. What does it mean, multi-master setup? It means that if I have 3 or 5 nodes in the cluster, each one of them can accept writes at the same time. And this is by design. The RavenDB subscribed to the philosophy is that if you wrote something to the database, you probably meant to do that and don't want to lose the data. So RavenDB will accept the data. In some cases, if you have an update to the same document at the same time on different nodes, it can create a conflict. There is a way to handle that here. I'm not touching that. I think that I spoke about this a few times in other webinars. RavenDB also have support for compare exchange values, which allows you to do a distributed interlocked operation that is guaranteed to be safe. With Mongo, on the other hand, Mongo uses a single master system, which is using the RAF protocol. I'm actually credited on the implementation, which was very funny about that. But the model in which they are working is quite different. They have a master that is selected using the RAF protocol. They run all of the operations through the oplog, but there is a few issues here. First of all, there is the recent Jepsen report, which calls out some of the MongoDB guarantees around transactions, i.e., according to the report, they didn't find that they're able to actually get proper transaction support. But another issue here is that if you have network disturbances, it's easy to get in a situation where you're unable to proceed. The other issue that you have to take into account is that in terms of the topology that you have on the system, you have to deploy multiple processes and nodes in order to create a cluster. With RavenDB, all of the nodes are running the same software. They are entirely homogeneous. It makes things easier. Sorry, this is a somewhat open-ended question, so I'm trying to answer that as much as possible. Okay, we have from Josh, we have a problem that doesn't lend itself to MapReduce. I'm wondering how we might approach it in RavenDB. We have records that flow in that have a machine state value. The value is typically one of online running pose. It doesn't necessarily change on each record. We need to know the current state, which is an MapReduce problem, reduced to the most current record. However, we need to know how long the machine has been in that state. So we need to know the time of the first level that changed the state, and then we can compute now. Okay, so that's an actually really interesting problem. Thank you. So let's see if I understand that. We have this. Running, something like that. And now we have state 2, sorry, at I think this is correct. Okay, and let's go here and add this yesterday. Now we need another one. Something like that. Okay, so if I understand that, what you want to know, okay, I have a report, let's say, every day, and I want to know what was the duration of the last error. And let's see, let's start from the first issue, from s-index.states, s.at, s.state. Okay. So what I'm doing, I'm outputting here the fields on the map that I'm going to get out. And here I'm reducing that by the machine because this is what I'm actually generating. Why do I even have Java installed? And now machine equal.g.key. And now I have something like this. Let last equal order by descending state last dot at. So if what's yes. Okay. So if I did this properly, this is what it says. Now you want to know how long it spent getting stacked. So what we can also do is to say something like that, you know what? Let's find the previous state. In this case, I'm basically just going to say, you know what, let's just, here we have the previous states. But now we have to aggregate that. And this is the last, so let's do a and now here is what we want to do. We want to here do the computation on the state change. And I'm just going to do the last one, but it generalized nicely. So sorted last state. And now sorry, easier to do. Something like that. It's going to show up at something like this, basically. It's really complicated at this point, but that's the idea. I see where this is going, but is it not relying on the messages entering the system in order and also RavenDB process them in order? No, it does not. That's the whole point of doing this, because what I actually need to do, I need to say, okay, what is the last known two state changes here? And then instead of operating on this, I'm going to do something like, okay, let's also take into account the items that I have in the pref state. So what I would technically need to do, I would need to do something like something like this. Horribly complex, but it does the right thing. More questions, people? Interesting MapReduce problems are lots of fun, especially because you're not necessarily going to think, oh, this is an actual MapReduce issue. But every time that you have some data and you want to aggregate that, MapReduce is very applicable. Let's see, I think we have one more. Okay, so no more questions. Thank you very much. I'll remind you that right now I'm running locally on debug edition, but you can run RavenDB on the cloud. You can see it here. If you have, we actually recently added both the GCP and some additional, I think that was the Africa one, the additional regions in AWS. If you have any questions, remember, we're always happy to answer questions in the mail list. If you have anything to chat about, there's also the live demo. You can request that, and we'll be very happy to set you up. And thank you very much. Have a great day.